For our next section, let's take a look at the concept of solution curves without a solution. We've seen that the solution of a differential equation has a curve that is essentially its graph, but that has one major difference between the graph of a normal function and the graph of a solution to a differential equation, and that is that our solutions cannot have any discontinuities. A solution to a differential equation must be differentiable, which means it must be continuous. We will, in upcoming sections of this course, begin actually solving differential equations explicitly and in some cases implicitly. However, with a very particular subclass of differential equations, which are relatively simple compared to others, you can actually talk about the solution curves and say something about the solution without explicitly finding the solution itself. In this section, we'll be taking a look at those kinds of problems with a definition here. Let's talk about what we mean by an autonomous equation. So an ordinary differential equation, an ODE, ordinary differential equation, is said to be autonomous if the independent variable does not explicitly appear. So if everything's a function of x, the x itself never makes an appearance. Or if everything's a function of time, everything's a function of t, t never makes an appearance. Does not explicitly appear in the equation. Okay. If x denotes the independent variable, and of course it can be other variables, but we'll use x as the example here. If x denotes the independent variable, then the autonomous first order equation, then an autonomous first order equation would look like this. Can be written f of y and y prime. So using only y's and y primes, no actual x's, you could write your equation equals to 0. Now, of course, both of these are functions of x, but x is never explicitly there. Of course, you can always write the y prime isolated, so you could also write this as y prime equals f of y. So for an example, if I have y prime equals 1 minus y squared, or if I were to write it in Leibniz notation, dy dx equals 1 over 1 plus y, both of these are autonomous. And first order because the highest derivative is 1 here. You want something that's non-autonomous, then the x appears explicitly in the problem. So for example, if I had y prime equals y times the sine of x. Or in Leibniz notation, I could say dy dx equals 1 plus y over 1 plus x. That's not to say these can't be solved. It's just that these are not autonomous. These would be handled in later parts of the course. Are not autonomous. Autonomous. Okay. Note that in practice, physical models that do not change in time, and therefore they're independent of, thus they're independent of their independent variable t, are autonomous. If something doesn't change in time, that's usually what we mean by autonomous. So, definition. Let y prime equal f of y, and we can use either one, but we're going to go with this one for now. Let y prime equal f of y be an autonomous first order ordinary differential equation, and let's have C be some real number for which f at that c is equal to 0. It's a 0 of your function. Then c is called a critical point. Or sometimes it's called an equilibrium point. Equilibrium point. Or sometimes it's called a stationary point. And these are all interchangeable. It's either called the critical point, equilibrium point, or stationary point of the equation. So for example, and this really is about as simple as it sounds, it is just, you're back to algebra. The question is, find all critical points, find, I lost a letter there, find all critical points of y prime equals y squared plus 4y plus 2. Okay. All right, so if y prime equals a function of y, then whatever number makes the f of y equal to 0, that's our critical point. So what we want to do is we want to take this part over here, the part that doesn't have the y prime on it, and find its zeros. Okay, so we find all values of y such that y squared plus 4y plus 2 equals to 0. We're back in algebra. We could factor here. We could use the quadratic formula. We could complete the square. Quadratic formula sounds simple enough. Let's do that. So here we're going to have that our critical points are going to be c equals negative 4. I'm going to use the quadratic formula here. Negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 2 all over double the value of 1. Quadratic formula, negative 4 plus or minus square root of 4 squared minus 4 times 1 times 2 all over double the value of 1. And so this gives us 16 minus 8 is 8, so negative 4 plus or minus root 8 over 2. The square root of 8, that's the same as the square root of 4 times 2, which is the square root of 4 times the square root of 2, which is 2 root 2. So here I get negative 4 plus or minus 2 root 2 over 2. And since everything's even, I divide by 2, and I get that my critical points are going to be given by negative 2 plus or minus root 2. Okay, so it looks like I've got 2 of those. Here I will label them separately, although we can write it as plus or minus. I'll label them separately. Here I'm going to have, so we have 2 critical points. I'll call them C1 and C2. So C1 is going to be negative 2 plus root 2, and C2 is equal to negative 2 minus root 2. So here we see an example of what we mean by critical points. Okay, so what about a critical point? Well, we have a theorem. I think I can fit that one down here. This is a very short one. Theorem. If you let C be a critical point of a first-order autonomous differential equation, let C be a critical point, or whatever other label you want to use, critical point of the first-order autonomous equation y prime equals f of y, then, then the constant function y of x equals to c is the solution to that equation. Like that. So from our previous example here, we can see we have two solutions. We have two critical values to finding where this is equal to 0. Okay, then if y at x equals 2, what did I have? Negative 2, right? Yeah, negative 2. Negative 2 plus root 2. Then y prime at x equals to 0. All right, after all, if this function is a constant, there's no variable here, this is constant, the derivative of any constant we know is 0. All right? But we already know that f of y is equal to 0 at negative 2 plus root 2, right? Because that's what we found over here. That function is equal to 0 at that number among a couple of them. So y prime is equal to 0 because the derivative of constant is 0. F of y is 0 because that's how we found this in the first place. We found what made f of y equal to 0. So y prime and f of y are both equal to 0, which means they're equal to each other. And that's a solution to that differential equation. More simply, we go back to your original equation. This number, plug it in here, makes this 0 because of the quadratic formula. Plug it in here, the derivative of any constant is 0. So 0 equals 0. Yeah, that's a solution. And the same thing would happen for the other one. So if you have any critical number, then that critical number is itself a solution to your problem there. Now you might look at that and say, well, yeah, that does work, but isn't that kind of a cheat? Or at the very least, isn't that kind of a trivial solution? I mean, you're plugging in a number, and just kind of by definition of how derivatives work for constants, 0 is equal to 0. But that doesn't really tell you anything about your function, does it? Like, did you actually find the solutions? Well, yeah, I found 2 of them. Well, yeah, but I mean, aren't there going to be other solutions? And aren't they going to be functions? Aren't they actually going to be something other than just constants? After all, earlier you said that unless you have an initial value problem, solutions to differential equations come as families. There's going to be a lot of them. Here you found 2, which, okay, that's nice, but isn't really that much. Okay, so let's expand on this. Okay, so in general, if you have y prime equals f of x comma y, if you have that kind of differential equation, you're going to get a solution. Y equals some function of x. I could say y equals f of x, but here we'll just be a little more direct. Y is the function y of x, which, again, by definition, is necessarily differentiable because you have to be able to plug it into a differential equation, which is differentiable. And thus continuous on its interval of definition. Was continuous on its interval of definition. All right, well, since it's continuous, that means that just, what do you call it? Not informally, that's the word. So informally, that means it doesn't have any breaks, doesn't have any jumps, there's no tangent lines anywhere on there, right? That's what we mean by continuous in an informal way. So then that means that for every point along your solution curve, the slope is going to be given by y prime equals f of x, y. In fact, let me write that here. So since Yeah, so since our solutions are continuous, at least as long as they're in their interval of definition, then they don't have any breaks, no jumps, no holes. And thus, they have a tangent line along every point. Along their entire domain. You don't have any place where the derivative is undefined. You don't have anywhere where there's a vertical asymptote or anything like this along their entire domain. Whose slope is necessarily given by y prime. Oh, but you began the problem by noting that y prime was equal to f of xy. So the slope, whose slope is y prime equals f of x comma y. So this equation is not just something to solve, it's descriptive of the curves themselves. It's saying whatever solution there is to this differential equation is described by this equation, giving us the slope everywhere along the curve. Okay, so if we evaluate f of xy, for every xy in a region in the plane, for example, for each xy, x comma y, and draw a line segment. Draw a line segment of the tangent line at each point. By the way, these little tiny line segments, these are called lineal elements. Lineal elements. For each point, we get what's called the direction field, or also sometimes called a slope field. We get a direction field, or also sometimes called a slope field of the ODE. Y prime equals f of x comma y. So the way that would look, and I'm not going to go through an example where I compute all of them, but just as a visual, let's say you had some equation y prime equals f of x comma y. What you could do is you could take the plane and say, okay, at the point 1, 1, I know I'm going to have some curve that's going to cross through 1, 1. You say, how do you know it's going to cross through 1, 1? Because we have an entire family of solutions, right? So every point is going to get covered, not necessarily by the same curve, but some curve is going to go through this point. Some curve is going to go through this point. Some curve is going to go through this point. So at any point, you can find a curve that goes through it, right? Because you have an infinite family of solutions for this problem. So what we could do is we come over here and say, well, look, the point 1, 1 is a point on one of my curves. I don't know which one, nor do I care for now. It's a point. Okay, so plug 1, 1 in here. Okay, what do you get? Oh, I get 2/3. Oh, well, whatever curve goes through here, at this point, the slope is 2/3. Okay, plug in this point. Okay, what's that point? That's 2, 1. Okay, plug 2, 1 in here. I get negative 2/3. Okay, well, whatever curve goes through here, there it is. There's the slope. So I get this little tiny piece of my curve. I don't know what the curve looks like as a whole, but I get this little tiny piece right here. And what happens is if you do this enough times, which this is definitely a very inefficient way to consider differential equations, but it is not wrong. If you do this enough times, you get what's called a direction field or a slope field, which, if you've taken Cal 3, it should remind you of something like a vector field, where you can consider little bits and pieces, which eventually, if you have enough of them, you might think, oh, my curve's got to go this way, and then this way, and then this way, and you can connect your points and get a visual of the direction, path, and general form of your solution curves to your differential equation. Okay? So even without knowing what the solution is, you can create a good sketch, point by point, linear element by linear element, of the entire curve. Oh yeah, but you said this is really inefficient, right? Oh yeah, you'd have to find hundreds or thousands of points just to get a good illustration of what's going on. Unless you have an exceedingly simple equation, you do need a lot of information to get a curve. However, we did just look at a very simple type of problem, the autonomous problems. So now let's consider those in the context of a direction field. Let's go ahead and consider the autonomous equation. That looks like, and here I'm going to do this very generally. I'm not going to have any specific numbers just now. I'm just going to go ahead and plug things in with placeholders like A, B, and C. So let's say you have an equation y prime equals y times ay minus b. It's an autonomous equation because the x never appears here. First order, so it does fit the category of problems that we were looking at a few minutes ago. Okay. Here, a and b are not known to us, nor are we actually even going to care what they are, but they're just numbers, where a and b are constants. And here we want them to be positive. Kind of limited. Certainly most equations won't look like this, but here, again, we're starting off with very simple ones that don't have a lot going on. So if you have a first order problem, and it's autonomous, and you have positive constants that look like this, consider what happens in the context of a direction field. Okay? Then, f at y, well, the way autonomous equations are written, y prime equals f of y. So f of y is all of this stuff. It's ay minus b, y minus b. So the critical points are whatever makes this 0. Y equals 0, and y equals 2a minus y. Ay minus b equals 0. Right? If y is 0, the whole thing's 0. If ay minus b is 0, the whole thing is 0. And here you can solve for y. You can add the b, divide by a. Add the b, divide by a. So here I have my two critical points. Okay, cool. So I know that these two are solutions. Y equals 0 and y equals the fraction b over a are solutions to this differential equation up here. But we can say a lot more than that. Let's go ahead and place these on a vertical line. A vertical line? What vertical line? Well, a vertical line. Place these on a vertical line. Kind of like a number line, but it's going to be up and down. Wait, I thought number lines were always left and right. Well, usually they are, but we've seen one place where number lines are vertical. It's the y-axis. Here, what you want to visualize is that this is like the y-axis. Well, what happened to my x-axis? I'm going to draw it here for now, just for the visual, but we're not actually going to care about it. Just the y-axis. Well, okay, why do you have an x and a y-axis all of a sudden? Well, just like before, we're going to consider a slope field, which we're going to consider over a plane. Oh, okay, so that's your plane, but why do you only care about the y value? Because here, y equals 0 and y equals b over a are constant functions, which means they are perfectly horizontal, which means they don't go up or down. Right? They stay perfectly flat. So as long as I know where they are on the y-axis, I know where they are everywhere. If I know it crosses right here, well, then I know it goes on forever along that line. So here, we don't actually need this one. If it makes you feel more comfortable, you can draw it in there, but we don't need it. Here, our critical points are going to be at 0 and at b over a. Okay, cool, but that doesn't really do much, right? You found your 2 points, you label them on a graph, and I guess, yeah, that does tell me that this graph is a solution curve and so is this one. But what's the point? I mean, you haven't done anything different than what you did in the last problem. You still just found 2 solutions. Well, we actually find a lot more than that. Because now consider this y-axis as being split into 3 parts. There's 2 numbers on that number line, which means it's split into 3 parts. Part 1, part 2, part 3. Okay, so what? Well, now consider the following. If we have some values, any point in this interval, okay, well then that's somewhere between negative infinity and 0. From down here, from negative infinity to 0. If we have something in this interval, it's somewhere between 0 and b over a. Okay, so from 0 to b over a. And if we have something in this top interval, well then that's something greater than b over a. So starting from b over a, going off to infinity. Okay. In the context of a slope field, whenever you plug some point into your equation, it's supposed to give you a slope. Well, let's see what happens when we plug something in from each of these intervals. Again, all I'm really doing is I'm saying I've got my xy plane, and I'm going to pick some point from here, from here, from here. It doesn't matter, as long as the y values are between 0 and b over a. Do my x values not matter? Well, we don't have anywhere to plug in x. This is an autonomous equation. X's don't appear. So no, we don't care what happens to x. That's why we only need the vertical axis. Again, if it makes you feel better, you can put the horizontal axis. Otherwise, we don't really need it. So if I pick some number between here and here, let's see what happens to f at y. Okay, well, if I pick from negative infinity to 0, and I plug it into this equation here, I'm plugging in a negative number. My y will be negative. Okay, well then this is a negative number. And then this is a negative minus something, because remember a and b are both positive. So a positive times a negative is a negative. A negative minus something, that's even more negative. And then that's a negative. So if I plug in any negative number, I'll get a negative times a negative, which is a positive. You say, well, what positive? I don't know, but whatever it is, it's got to be positive. Okay, so what? Well, an autonomous equation, the y prime has to equal that f of y. So if f of y is positive, the y prime has to equal that. So it must also be positive. Okay, so what? Well, y prime is a slope. Think back to Cal 1. Think about like the first derivative test. Think about what we mean by increasing and decreasing. If y prime is positive, that means the function y, that this is the derivative of, the function y must be increasing. So my solution curve must be increasing. Okay, so what does that mean? What it means is that any solution curve that existed below the x-axis, anything that happens below y equals to 0, will have a positive slope, which means all my curves have to look something like this, going up. Okay, so they're going up. I guess that's more information you had before, but can you say anything else besides that? Yes, in fact. Let me go ahead and fill in the rest of these, and then we'll actually say something even more about these solution curves. Here, if I plug something between 0 and b over a, okay, well, a and b are both positive, so between 0 and a positive, that's a positive. Okay, so I'm plugging in a positive number that's less than b over a. Okay, well then, that'll be positive right there, because I'm plugging in a positive number, so y is positive. But if I plug in a number that's less than b over a, and I multiply by a, the denominator cancels out. Right? The a's cancel out, and I'm left with something that's less than b. Right? If the number I'm plugging in is less than b over a, cancel the a, well then I'm left with something less than b. And if I have something less than b minus b, well that's a negative. Something less than 10 minus 10. Something less than 1 minus 1. That's a negative. So I have a positive number times a negative, which is negative. But if that's negative, y prime has to equal to this one, so that'll be negative. And whenever you have a negative slope, that means your function is, by definition, decreasing. Okay, so any of my solution curves that exist between here and here, it doesn't matter what point I take, they're all decreasing. So I'll put a little arrow facing down right here. All my functions go down. Okay, what about this one? Okay, well, if I pick a number greater than b over a, that's definitely positive. Something bigger than a positive number is positive, so that first number is positive. If I take something bigger than b over a, and I multiply it by a, the a's cancel out, and I get something bigger than b. But if I take something bigger than b, and I subtract away b, I get a positive. It's going to be a smaller positive, but it'll be a positive. So, plugging in something between b over a and infinity gives me a positive times a positive. That's a positive. But that's got to equal to that one. Right? Y prime equals your f of y. So that one will be positive. And because you have a positive slope, that means your function is increasing. So here, this is going to be going up like this. Any solution curve that exists above this line will be increasing, always up. Okay, so what? That means these lines here are going to serve as reference points to all of our other solutions. Wait, what now? Yeah, look. All of my solutions have to be increasing here, right? Yeah. Oh, but here, this solution is flat. Okay, so if I were to draw out a solution, if I were to draw out this solution, this one's a constant. And same thing here, this one's a constant. Here, my solutions have to be increasing. Oh yeah, but they can't cross each other, right? Because with an initial, like with an initial value problem, if you have an initial condition, if you have a single point on your curve, that single point should uniquely determine your curve, which means that I don't have any points that are shared between curves. So if I have any curve that exists below this line, it has to be continuously increasing, but it can't touch this line because then it would share a point. Oh, I'm back in algebra. This is called a horizontal asymptote, isn't it? So any of my solution curves, even though I don't really know what they look like, I kind of know what they look like. They all go like this. Same thing here. These all have to be decreasing, but they can't touch this line. Okay, so all my solutions got to look something like this. And I don't know the exact details. Maybe this is a little too steep. Maybe it's a little too shallow, whatever. But it's going to go this way. Oh, you know what? I messed this up over here because they can't touch this line either. So they're going to look something like this. Kind of look like arctangents, don't they? Something like that. And over here, these all have to be increasing. So they'll look something like this. Never quite touching that line. And so just these two lines and a few arbitrary test points saying, okay, here's what happens between here and here, here and here and here and here, I now have a very good visual of what my solution curves are going to look like, at the very least in a broad, not detailed way. Sometimes that's all you really need. One thing you might notice here is that all of our solutions are tending toward this line. Look at that. As we go toward the right, all of our solutions are coming toward this flat line. Whenever you have something like that, whenever you have a horizontal line that it acts as an asymptote, but all of our solutions go toward it, that's called an attractor. On the other hand, here, you have a horizontal line that acts as an asymptote, and as you move to the right, your solutions are moving away from it. Notice everything's going away from this line. That's called a repeller. So here we end this with a little bit of vocabulary. This whole thing, this chart right here along with this set of graphs, this is called a phase portrait. And it allows you to get some intuition as to what the solutions of your differential equation might look like without explicitly going through the computation of actually finding these. I never found the equations to any of these except for these two flat ones, but I still have a decent understanding of what the solutions should look like. So this is a phase portrait. I don't know why I pluralized that. Phase portrait of my y prime equals y times ay minus b. And this is somewhat limited. It would be a lot harder than this to find a phase portrait for some equation in general, for some differential equation in general. But here we're starting off with something nice that doesn't take a terrible amount of effort to do. Where this equation here, as you go to the right, all of your solution curves are going toward it. You say, well, to the left, they're going away. Yeah, but we label these based off what happens on the right side. So here, y equals 0 is an attractor. Which is asymptotically stable. What do we mean by asymptotically stable? You mean as we move toward the right, everything is going toward it in the same direction from both sides. And y equals b over a, this other asymptote up here, everything's moving away from it. This one is an attractor, which is asymptotically stable. Here we have something that's asymptotically unstable. Or let me do it in the same order. This is a repeller. It's a repeller, which is asymptotically unstable. The phrase attractor and repeller are obvious. Attractor because it attracts them, repeller because it pushes them away. Asymptotically stable and asymptotically unstable are a little less obvious. What we mean is, let's say I have a solution that's on this point. Okay, well, it's going to follow this line. Okay, well, let's say we had a solution that was near this point, but not exactly there, slightly above. Oh, well, it's still going to more or less follow the line. Oh, I mean slightly below. Yeah, still going to more or less follow the line. So it's stable. Even if you don't hit the point exactly, as long as you're somewhere nearby, because this line is an asymptote of all the things nearby, it's going to follow that line anyway. So there's a stability to that answer. You're going to follow this one way or the other. This one's asymptotically unstable, because if you land on this point, okay, you're going to follow this line. But if you land even slightly above or slightly below, you're definitely not going to end up on this line. You're going to end up far away. It's going to go up or it's going to go down. Asymptotically unstable, because you're not approaching that line ever again. Unless you're on the line, you're never going to get anywhere near the line. So unstable. Note, even though it's not drawn here, if a critical point is an attractor on one side, from one side, and a repeller from another, from the other side, it is called asymptotically semi-stable. Semi-stable. So as a visual, you would have something that, okay, here's your line. From one side, things go toward that line, but on the other side, things move away from that line. So it's semi-stable. If you were on this line, you're going to stay on this line. If you're slightly above the line, okay, you're still going to stay on that line. But if you're slightly below, it's going to move away from your line. And it doesn't matter which direction. So you could have one from the other side where, okay, here it's moving away as I go up, but it's moving toward as I come from the bottom. Either of these, as long as it's going toward it in one side and away from the other side, here toward it from the bottom and away on the top, either of these will be examples of being asymptotically semi-stable. All right, and that is it for this section as well as these definitions. Starting in our next section, we are actually going to start finally explicitly solving differential equations. All right. Hope everyone has a nice day, and I will see you all next time.